Welcome back to the deep dive. This is really your essential study guide where we take complex aviation source material and we'll try to make it crystal clear, actionable knowledge for you. Today, our focus is absolutely on you, the learner, especially as you're gearing up for those, let's face it, demanding ATPL theory exams, our subject. An instrument pilots use constantly, but maybe don't always fully grasp internally. The vertical speed indicator, the VSI. Now, in the cockpit, vertical speed is just, well, it's everything, isn't it? We need to measure climb, descent, control that vertical velocity precisely. And sure, the altimeter gives you a rough idea of altitude change, but trying to use the way that pointer moves, its angular rate for real precision.
Yeah, it's just not sensitive enough.
It really isn't. The resolution's poor, the lag, it's significant. If you're flying a complex approach, maybe needing that perfect 800 feet per minute descent to nail the glide slope.
We're navigating busy airspace.
Exactly. Where ATC dictates a precise height loss on an airway. You just have to have the VSI's accuracy. You can't eyeball it with the altimeter alone. So our mission today, tear this instrument apart, really understand the physics behind it, pinpoint its weaknesses, its operational limits, and crucially, and most importantly, distill every single point into a solid fact you can recall for your exams. That's the goal here.
That's absolutely right. We're drilling down deep into how vertical rate is actually measured. The VSI, or you'll often see in textbooks as the RCDI, rate of climb and descent indicator.
Right, RCDI.
It looks simple on the outside, doesn't it? But inside, it's surprisingly complex, cleverly engineered. So the plan is, we'll systematically cover the core principle, that differential pressure idea. Then the genius bit, how it compensates for altitude in its construction. We'll definitely focus on the errors, the limitations, especially that time lag that causes so much grief. That's a huge exam topic.
The time lag, yeah. Always comes up.
And then finally, we'll look at the instantaneous VSI, the IVSI, and how it tries to fix those inherent problems. Think of this whole deep dive as your focused study session, your shortcut, really, to mastering this specific instrument for exam day. Every point we hit could be a question.
Okay, let's get into the nuts and bolts. The core mechanics. If the VSI isn't directly measuring an angle or g-force, how does it figure out vertical movement?
It's all about pressure, specifically static pressure, that constant physical property of the air surrounding the aircraft. The VSI senses the rate of change of that static pressure. It's fundamentally a comparative device, and it's built around a deliberate time delay.
Right, that time element you mentioned, that sounds absolutely central to the classic VSI design.
It really is. The VSI gets its reading by comparing the current static pressure with the static force of feeding it right now with the static pressure the instrument was seeing or was exposed to roughly, say 4 to 6 seconds earlier.
4 to 6 seconds, okay.
Yeah, that controlled, sort of artificially maintained time difference, that's the engine driving the VSI pointer.
Yeah.
Without that built-in lag, you just couldn't measure the rate of change using differential pressure alone.
So that 4 to 6 second lag, it's the core principle, but as you hinted, it's also going to be its core weakness later on, right?
Exactly. We'll definitely circle back to that. So when the aircraft starts climbing or descending, the static pressure outside changes, well, pretty much instantly.
Okay, so how is the instrument actually built to create and maintain that necessary delay inside itself? Hashtag tag 1.2, the restricted system.
Well, the construction is a neat bit of passive mechanical engineering. You've got an airtight case, think of it like a sealed can, and inside that case, there's a pressure-sensitive capsule. It's quite similar, actually, to the aneroid capsules you find in altimeters, designed to expand and contract with pressure changes.
Okay, airtight case, inner capsule.
Now, crucially, both the inside of the capsule and the surrounding case get fed static pressure from the aircraft's static system.
Hold on. If they're both getting the same static pressure feed, how does that create the difference, the differential pressure you need?
That is the clever part. It's all about the restriction, the static pressure going into the capsule. That's instantaneous. It gets in quickly through a normal connection. However, the static pressure feeding the air...
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best